Hi everyone, in this video we're going to talk about section 2.2, which involves the axioms of probability. So before, we were just talking about sample spaces and events. And so we weren't really talking about the probability of sample space, probability of events happening. But that's our main interest here. And so let's start by talking about the probability of an event. Okay, so for some sample space, script S, the probability of an event A is denoted P of A. And so if you look at this and you're familiar with function notation, which means you're probably familiar with something like f of x is equal to 2x plus 5. Yes, this is a function as we're used to, where f is the function. Now we have the same thing where instead p is the function. Okay, so p is a function, but it's a weird function that we really don't need to get into. Okay, and you usually don't until something like graduate school. But it is a function. It operates on an event A. The input is a number of outcomes, and then the output is a number. Okay, and we know sort of intuitively that there are some truths about this number. It can be in a certain range, which we know to be 0 or 1. Okay, you can't have less than 0 of probability. 0 probability is that it won't happen. Okay, and 1 probability is a certain event. It will happen. Okay, so you can't give more than 100% doing anything, contrary to what a sport says, and you can't give less than 0%. So that is what I mean by sort of axioms of probability. So we have this function P, and the axioms, there are 3 of them, and they tell us how probability behaves. Specifically, these are called the Kolmogorov axioms. Okay, if we want to be specific. And so the first axiom is going to be intuitive for us. For any event A, the probability that that event happens is non-negative or greater than equal to 0. I can't have a probability less than 0. The second axiom is that the probability of the sample space is equal to 1. Okay, hopefully this should make sense as well. If I have the sample space represents everything, and so the probability of anything in the sample space, or the probability of the entire sample space, has to be 1. Okay, so everything has to add up to 1. And so this also gives us sort of a secondary axiom. Sorry, we'll get rid of that stuff up here. And if we call this number 1 and this number 2 really gives us another restriction on A. The probability of any event A has to be also less than or equal to 1. Okay? If everything, the probability of the entire space is 1, I can't have a subset of that having greater probability. So it gives us that second one there. Okay. You already know all this in your mind. This is just sort of formalizing it. And then we have a third one. And this one is quite tricky. And so I put it here for completeness, but you don't need to really worry yourself about this. It says if A1, A2, A3, so on and so forth, is an infinite collection of disjoint events. So if you remember back before, disjoint events means they have nothing in common. Okay, so if I have an infinite number of disjoint events, then the probability of the union of those disjoint events is equal to the sum of the probabilities. Okay, and so you're wondering what the heck that means. We don't need to worry ourselves really about that. Okay, they would call this in language, it's closed under countable unions. Okay, but again, we don't need to worry about that. So that's just a fun fact there. Closed under countable unions. Now, those axioms give us or give rise to some more properties of that P function that we know intuitively to be true. Okay, and so those new properties and rules that we know to be true is that for any event A plus A complement, so the probability of A plus the probability of A complement is equal to 1. Okay, and so that sort of arises from the fact that if you take together A and A complement, that makes up that sample space S. Okay, sorry for my bad writing. If you're in A or you're in not A, and so A plus not A is the sample space, and so since the probability of sample space is 1, then the probability of A plus the probability of A complement is equal to 1. Now this is important because you can move around the pieces here and get something like the probability of A is equal to 1 minus the probability of A complement. Okay, so if the event A is the probability that I pass this course, okay, and I don't really know that probability, but for some reason I know the probability that I don't pass this course. Okay, that would be A complement, right? You either do or don't pass the course. A complement would be not passing the course. I could use this formula to get at A, even though I don't know it directly. Okay, so hopefully that makes sense. So that's 1. There's that second rule that I talked about on the previous slide. From that sort of probability that the sample space is 1, we know that the probability of an event A has to be less than or equal to 1. And then it leads to what I'll call the general addition rule. Okay, general addition rule. Finding the probability of a union. So the probability of a union, A or B, is equal to the probability that A happens plus B happens minus the intersection. And so this is a common thing that people see and wonder why you're subtracting away. Sorry, let me take away my previous writing. Why are we taking away this union? Well, if you think about it, if we draw our Venn diagram, which I'll draw fairly poorly there, this is A and this is B. When we say A or B, we collect A here, right? And we collect B here. And both of them include the intersection. And so essentially we're counting the intersection twice. And so we need to subtract away that intersection once to get the proper thing. Okay, so hopefully that makes some sense. And then we can even be fancier, and we can talk about the general addition rule for more than 2 variables, and we'll go up to 3. Okay, and so it's quite enough to think about 3 of them, but of course you could go farther, more of them, but of course we'll only go to 3 here. Okay, so A or B or C. We do the same thing as we did before, but there's sort of more housekeeping here. Probability A plus B plus C. Okay, so that's going to encapsulate most of it, but then, of course, we've overcounted on the intersections. So we subtract away each of the intersections once, A and B, A and C, and B and C, the different combinations. And then, unfortunately, when we do that, then we've taken away a little bit too much, and we need to add in back the intersection of all three. Okay? And so these general addition rules can help you in certain situations when you're trying to find probabilities and you have partial information, but you don't have all of them. So let's do an example. In a certain residential suburb, 60% of all households get internet from a local cable company, 80% get television service from that same company, and 50% have both services from the same company. All right, so if a household is randomly selected, what is the probability that it gets at least one of the two services? And then what's the probability that it gets exactly one of the two services? So in order to solve this, we first need to write down our events, okay? And we need to write down the probabilities that we already know. And so I'll use A and B, okay? But of course you can use whatever you want. I'm going to let A be internet. I'm going to let B be cable. Okay? And so what do we know? We know that they're the same company, so I left off some information on A and B. Of course, you should write out the full thing, but for simplicity's sake, I just wrote internet and cable. But hopefully that makes sense. The probability that you get internet from this local cable company is 60%. So the probability of A is 0.6. I'll always write probabilities in decimals and not percentages. Okay, so always decimals, never really percentages. The probability that you get cable from this company, or the probability that B happens, is 0.8, and then you get both, so that's A and B, so I would write that as A intersect B is 0.5. Okay, and so now we have our partial information. We're going to use the rules that we just learned to try to get the information that we want. So if a household is randomly selected, what is the probability that it gets at least one of the two services? So how would you write that out? I guess there's a couple ways that you can do that. At least one, that's A or B or both, right? So you can get at least one means one or more. And so that could be A or B or both. And it turns out that the union of A and B meets that criteria of at least one in this case where there are only two events that we're considering. So we want to find the probability of A or B. And so lucky for us, we just learned about the general addition rule, which says that the probability of A or B happening is equal to the probability that A happens plus the probability that B happens minus the probability that both happen. Okay, and so that's 0.6 plus 0.8 minus 0.5. So 0.6 plus 0.8 is 1.4 minus 0.5. That gives us 0.9 or 90%. So there's a 90% probability that if I randomly select a household, that household is going to have at least one of the services. Okay. Now, what is the probability that it gets exactly one of the surfaces from them? So how would we write that? We'll call this number 2. Exactly one of the surfaces. So it can be either A or B, but not both. A or B, but not both. And so you can write that in a number of different ways. Again, like I said, I'm repeating myself. So it's the probability of A really A or B, right? But not both A and B. There might be a more eloquent way of doing that. But I think it's pretty simple. We know A or B from number 1, and that probability is 0.9 minus the intersection, which again we know, 0.5. And so that probability that you get one or the other, but not both, is 40%. Okay, and so quickly, what does this look like? Why is number 2 right? I realize that it might be a bit weird for you to think of that. If we have A and B, I am sorry for the bad Venn diagrams. We have A, B, and so if we do A or B, and I'm sorry if you hear my dog growling, he sees something outside. Sorry. If we look at A or B, that's going to cover A and the intersection, also B and the intersection. Okay, so our usual A or B, we take away one of the intersection counts. Okay, so maybe you get rid of the red. So if we're here, right here, okay, we get rid of the red part and leave the blue part, and that gets us A or B. Okay, so that's this right here. But we want exactly 1, which means A or B, but not both. Okay, we can't, exactly 1 doesn't mean both. So we need to subtract away that extra intersection that remains. So we got rid of the red first, then you can get rid of the blue intersection. Okay, here's the intersection, 0.5, and so then we get rid of both. That means you would clear out this intersection completely. So A or B, but not both. Okay, so that's how you do a type of example that you might see. Now, for your turn, here you're going to get something very similar. Suppose 55% of all adults regularly consume coffee, 45% soda, and 70% at least 1. Okay, at least 1. What's the probability that a randomly selected adult, sorry, it should be 1 adult, regularly consumes both? And then what's the probability that a randomly selected adult doesn't consume at least 1? Okay, so not at least 1. Okay, so that's going to be the end of this video and the end of section 2.2. Then we'll move on to section 2.4 next time.